To move 2 tons of mass down a highway at 60 miles per hour requires overcoming a continuous barrage of kinetic resistance. Modern electric and hybrid vehicles are ground-up electromechanical architectures designed to solve this physics problem through integrated system design. This free body diagram maps foundational kinetic demands: aerodynamic drag pushing the front, rolling resistance on the tires, and gradient forces pulling backward. These factors define the baseline power required, collapsing into a single curve that sets the force the propulsion system must generate every millisecond. To understand these vehicles, we must map the energy flow backward, starting from forces on the roadway, retreating through internal mechanical systems, and ending at the electrical grid. Building this system requires a sequential buildup, defining mechanical loads, selecting drivetrain topologies to deliver that load, matching electrical machines, and engineering energy storage to power it all. This multi-domain chain requires coordinating mechanical loads with electrical responses, creating a single interdependent engineering model. We start by moving inward from the external kinetic forces to the transmission, the mechanical hardware required to physically turn the wheels. The power requirements we mapped on the roadway precisely dictate the gear ratios and torque delivery curves the transmission must achieve. To satisfy those specific transmission characteristics, engineers select an electric drivetrain topology, a structural blueprint determining how power flows from storage to motion. This block schematic illustrates a pure electric traction drivetrain. The architecture is linear. Power flows from the battery block, through the inverter, into the electric motor, and straight to the transmission. In a hybrid traction system, mechanical output of a combustion engine merges with the electrical path. A series topology maintains a linear flow. The engine acts exclusively as a prime mover for a generator, feeding the battery or motor. The parallel configuration splits the architecture. Both engine and motor have independent mechanical links, blending torque at the gears. The series parallel topology uses a power split device, like a planetary gear set, to dynamically route power. The selection between these topologies relies on fuel efficiency analysis, mapping against the vehicle's expected load profiles, weighing highway cruising against urban stop-and-go driving. A drivetrain topology acts as a mechanical algorithm, dictating the efficiency at which stored energy translates into kinetic motion. Zooming into the traction motor reveals the specific internal electrical machines responsible for generating that massive physical torque. Engineers evaluate DC versus AC machines based on efficiency density, operating temperature ranges, and maintenance requirements under continuous high-load applications. This cross-section shows a permanent magnet motor. By embedding magnets directly into the rotor, surrounded by stator coils, it achieves a high torque-to-weight ratio suitable for most high-performance EVs. A switched reluctance machine uses a magnet-free, toothed steel rotor, rotating as stator coils are sequentially energized. While avoiding rare earth materials, the transition between poles generates jagged torque delivery, requiring complex control to minimize ripple. These AC machines must interface with the vehicle's primary DC energy source. Power converters provide the interface between the battery and motor. They act as a nervous system, modulating high-voltage DC power into precise AC frequencies. This interface must manage bidirectional power flow, rectifying AC energy from the motor during regenerative braking to charge the DC battery. Without the microsecond precision of these power converters, the raw rotational force of modern electrical machines would be uncontrollable for precise vehicle dynamics. To understand what feeds these converters, we look further back to the energy sources themselves. Energy storage is defined by a trade-off between energy density, which dictates range, and power density, which dictates the ability to discharge energy rapidly. This is a Ragone plot, mapping these characteristics. The horizontal x-axis tracks specific energy, while the vertical y-axis tracks specific power. Batteries and fuel cells occupy the high energy density quadrant, providing significant range but limited discharge speed. Ultracapacitors and flywheels provide massive power density for rapid acceleration, but hold very little total energy. Energy source hybridization combines these disparate sources to bridge the gap between performance quadrants. This allows the system to handle different demands, like steady-state highway cruising versus a sudden acceleration for passing. During highway cruising, the high-energy battery handles the steady baseline load. However, rapid acceleration or regenerative braking introduces a massive transient load exceeding optimal discharge rates. The ultracapacitor intercepts this spike, delivering power faster than chemical reactions allow. By handling these harsh transients, the ultracapacitor protects the chemical lifespan of the primary battery. The principle of hybridization extends to the storage architecture itself, balancing long-distance range with immediate kinetic demands. Moving out from the vehicle components, we reach the edge of the physical architecture. The vehicle interfaces with the electrical grid as an open system, relying on external infrastructure to replenish its storage. Selecting and sizing charging stations depends on the specific energy constraints and voltage requirements of the vehicle's storage system. This single-line diagram shows how a charging station conditions grid power. Electricity flows through a transformer and an AC to DC converter before reaching the output interface. This process conditions the AC grid power into the direct current required by the vehicle's battery. Advanced grid interfaces include stationary contactless inductive charging. Inductive charging must overcome the physical challenge of transferring high power efficiently across an air gap without significant energy loss. This circuit schematic illustrates how resonant and compensation circuit topologies on both the transmitter and receiver coils allow for efficient power transfer through magnetic resonance. From mechanical friction on the tires to the magnetic resonance of the charging pad, a modern EV functions as a unified, continuously optimized electromechanical loop.